Okay, so again, I'm going through the solution for the quiz I gave on the first day of classes. Here is problem 2, and I just did this in my own engineering paper instead of trying to write it on the quiz itself to make it a little clearer. Here's the problem. I've got a model for a battery, and batteries are not just voltage sources. That's kind of an ideal model of a battery, but what happens is a battery has something called internal resistance. And with that model, we can predict, or we can show or capture the actual performance of the battery, which is that as you draw more current out of the battery, the voltage at the electrodes goes down. It's not really a constant voltage source. And so this is an exaggerated model. Internal resistances are usually fractions of 1 ohm, not 8 ohms, but I wanted to put that in there because it made the math a little bit easier. So it's a 12-volt battery, so it might be, say, a lead-acid battery in your automobile or motorcycle. So I had 2 questions right off the bat. The first 3 sections are about open circuit and short circuit. Open circuit means it's not connected to anything, pretty much as I drew it on the quiz. And so what's the voltage and what's the current at open circuit? Well, open circuit is not connected. There's no current, but if you were to put a voltmeter across it, you'd read 12 volts here. There's no voltage drop across here because there's no current. So the answer to this is, at open circuit, what's the voltage? And the answer is 12 volts. Short circuit is just the opposite. We connect the 2 ends of the battery together with something that has very little or negligible resistance. That's what I see in this drawing here. I just drew a line representing a resistance-free conductor. Current will flow, and the voltage drop, all the voltage drops around this loop have to equal 0. So if we got 12 volts driving the current, that means there has to be 12 volts drop across this. The only other voltage the only other voltage drop in our loop must be a 12-volt drop. So 12 is equal to 8 times I. 8 is the ohm, the resistance. This is Ohm's law, right? V equals IR. So the voltage drop across the resistor is 8 ohms times I, the current. Solve for I, 1.5 amps. Very, very simple. The voltage that you would see if you were to put a voltmeter across that short circuit is 0. That's the definition of a short circuit. Okay, part D, I mentioned this in class. I made a mistake on the exam, on the quiz. I put 100 W, capital W in there. I meant to go back into Word and change that W into symbol font, which makes it an omega. So the question should have been, if you connect the battery to a 100 ohm load, not a 100 watt load, so a 100 ohm resistive load, what would the current be? And so part D here is the example. Is the diagrams. There's our 12 volt ideal source, our 8 ohm internal resistance, and our 100 ohm load. Basically, these add up. 2 resistances in a series just become 108. But I did here, this is Kirchhoff's voltage law, 12 volts on this side of the equation, positive. Then over on the other side, there's an 8 times I voltage drop across this resistor, a 100 times I voltage drop across this resistor. The sum of the voltage drops have to equal the voltage gain. So we have 12 equals 108 I equals 0.11 amps. Not many people got that one right. Well, not many people got it right because I didn't set it up right. Finally, this was on this last part of part 2 was charging a battery. This is something they didn't cover a lot in circuits, I suspect, and you really have to think hard about how systems, different electrical systems work when you connect them together. But that's a big part of this class, so that's why I did it. So we have the same thing. We have this voltage source here. We have an 8 ohm resistance. What voltage do we put on here? Now we're imposing a voltage from the outside to drive the current back into the battery at a level of 10 milliamps. And so what voltage here is equal to the voltage drop here plus 12. And this is part of the trick of battery charging. In these other problems, when the current was going the other way, the voltage drop across the internal resistance subtracts away from 12. Now it adds in. So the answer here is the battery charger is equal to 12 plus 8I. And we know I gave you I is equal to 10 milliamps, which is 0.01 amps. So the answer is 12.08 volts. That's the voltage you would have to do to make that happen. Let's just keep this going. I'll just do problem 3 at the same time. that was my trick question. I didn't expect anyone to really derive this, but some people remembered this notion that you maximize power transfer between two systems by matching their impedance. In DC, impedance is the same thing as resistance. In AC, it's not, and we'll spend some time talking about that in the next couple weeks. But for this part, we'll say we match impedance by matching resistance. You maximize power transfer by choosing a load resistance of 8 ohms. Let's prove that real quickly mathematically. So I keep R as a variable here, and I set up Kirchhoff's law saying 12 is equal to 8I plus Ri, and so we have 12 equals 8 plus R quantity times I. The power loss or power transferred or the power dissipated, however you want to say this, is equal to the power dissipated in that resistor, and it could be I times V, I times the voltage, or I squared R. I'll use I squared R because the mathematics works out best. So the power loss is I squared R, and I solved this top equation for I, which is 12 divided by 8 plus Ri, and I substitute that in. So combining this equation and this equation, we get P, the power, is equal to 12R over the quantity 8 plus R squared. We maximize P, we find the maximum P by taking the derivative with respect to the variable, in this case R, the resistance, set it equal to 0. So DDR of 12R over 8 plus R quantity squared equals 0. We have to go back and find the quotient rule. I had to look it up on Wikipedia, the fount of all knowledge. And we remember here, if you've got a quotient between two functions, the derivative is given by this little guy here. In this case, U, my numerator is 12R, V is 8 plus R quantity squared. And so I get this thing for the derivative 12 times 8 plus R quantity squared minus 12R to 8 plus R. I'll let you figure out how I came up with all those. Divided by now 8 plus R to the 4th power. Yeah, it's getting kind of ugly. But the good news is, since we're setting this equal to 0 and solving for R, that just drops out. So multiply both sides by this little polynomial raised to the R, and you get this equation. Just do the math, as they say. It comes down to R squared equals 64, and we get the answer, R equals 8. Nobody did this on the quiz, but like I said, several people knew enough to say, yeah, I'm pretty sure the right answer is 8 ohms. And one last thing, that mistake I made in problem 2, where I said it's a 100-watt load, and people really struggle to try to make sense of it. This demonstrates why it makes no sense. If indeed the maximum power transfer is when R equals 8, let's go back and look what that means. Well, that means that power, the maximum power we can transfer out of this battery, is what we get when R equals 8, and that's 8 plus 8 here, which is 16. So we have 12 times 8. You know what? I'm just going to do this math side. Hang on just a second. So it's 12 times 8 on the top, and that's 96, right? And 8 plus 8 in the numerator, which is 16, and we square that, right? So we have 96 divided by 16 squared. I'm going to have to just do this the hard way. 16 squared, 96, 6. So 256. I think I knew that. If you do any binary work, you should have jumped right to that. So 16 squared is 256. 19 divided by 256. I don't even have to, 96 divided by 256, that's less than 1. Okay, I'll let you figure out. I'll leave it as an exercise for the student, as we like to say, to figure out what exactly the maximum power transfer for this problem is. But it's a heck of a lot less than 100 watts. It's less than 1 watt. Okay, that's it. Thanks very much, and we'll talk to you later.